Safi next. In this video, I will talk about the experimental aspects of photoelectric effect and would like to begin it from Einstein's popularity. So, although the initial source of popularity of Einstein was his paper on special theory of relativity, in which he expressed some very conflicting ideas about time, speed of light, and energy. However, Einstein was awarded with Nobel Prize for his theoretical work for explaining the experimentally observed phenomena of the photoelectric effect. In fact, his explanation revolutionized our understanding of the nature of electromagnetic radiations. In order to understand the approach of Einstein to the explanation, I would like to begin from the definition of photoelectric effect. The phenomenon of electrons ejection from a metal surface when it is illuminated with electromagnetic radiation is called photoelectric effect. The ejected electrons are called photoelectrons and the resultant current is called photoelectric current. The characteristics of the phenomena are studied with the help of the simple apparatus you see on the screen. Two metallic plates noted by C and E and respectively known as emitter and collector are mounted within an evacuated glass tube fitted with a window. Light of certain frequency nu is allowed to pass through the window and strike the emitter surface. The emitter and collector are connected through a variable source of potential so that the potential between them can be varied, and the voltmeter and emitter are connected to measure the corresponding voltage applied across the collector and emitter and the current set up in the circuit through the micrometer A. It is very important to note that the potential difference between the collector and emitter is given by V equals V sub ext plus V sub cpd, where V sub x is the external voltage applied to the source measured by the voltmeter, and V sub cpd is known as the contact potential difference. If the emitter and collector are made of the same metal, then V sub Pd is equal to 0. And if they are made of different materials, then V sub Cpd equals W sub E minus W sub C, where W sub E is the work function of the material from which the collector is made, and V sub C is the work function of the material from which the collector is made. Now let us observe the behavior of the experimentally observed photoelectric current against different quantities. If we draw a curve between the potential difference V measured through the connected voltmeter and the photoelectric current I measured through the connected micrometer, a curve shown in the figure is obtained. This qualitative shape of the curve is in fact a characteristic of the photoelectric current and applied voltage. However, quantitatively different curves are obtained for different intensities provided the frequency of the incident light is kept constant. For example, the photoelectric current for two different intensity of the incident light having the same frequency are plotted against the potential. Now it is well obvious from these curves that the photoelectric current for certain positive value of the potential reaches to its maximum values, and that maximum value is known as saturated current. Now, as the potential difference between the collector and emitter is reduced to 0, we still have non-zero current for both the intensities. Moreover, when the collector is made negative with respect to the emitter, the current begins to decrease and reaches zero at certain fixed value of the negative potential irrespective of the intensity of incident light. That is, for all intensity, the current becomes zero at the same negative potential. This negative potential is called stopping potential and is usually denoted by V sub naught. Again, let me highlight by restating that this negative potential is independent from the intensity of incident light. Now let us understand why the decrease in current happens when the collector is made negative with respect to the emitter. So when the collector is made negative with respect to the emitter, an electric field pointing from the emitter towards the collector is set up within the region between them. This electric field exerts a force on the photoelectron towards the emitter, thereby retarding them to reach the collector. So only those photoelectrons that surmount the retardation can reach the collector and hence constitute current. At V sub naught, the photoelectrons with maximum kinetic energy are also stopped and thus the current drops to zero. This means that the photoelectrons ranging from certain minimum to certain maximum energy are emitted from the emitter. The maximum kinetic energy of photoelectron can be expressed in the form of a function of the retarding potential and can be expressed as Ke sub maximum equals E times V sub naught. This equation dictates that the maximum kinetic energy of photoelectron converts into electrostatic potential energy of magnitude E times sub V naught and is quite independent of the intensity of incident light. This is a very important characteristic of photoelectron and you must pay your attention to this equation. Now let us observe another very characteristic behavior of the maximum kinetic energy of photoelectrons. If the emitter is illuminated with lights of different colors or different frequencies, and the corresponding stopping potential or the maximum kinetic energy are plotted against the frequencies of incident light used, a plot like this one is obtained. This obviously shows a linear behavior between the plotted quantities, that is the maximum kinetic energy and the corresponding. In other words, this plot very obviously shows that the maximum kinetic energy of photoelectron depends on the frequency of incident light. That is, increasing the frequency of incident light results in increasing the maximum kinetic energy of photoelectrons. In other words, more negative potential is needed for stopping the photoelectrons of highest kinetic energy with increasing frequency of incident light. The graph also shows that no photoelectrons are ejected when the frequency of the incident light is lesser than a critical, which here I am representing with nu sub naught. This frequency is called threshold frequency and its value depends on the nature of the material from which the emitter is made. It can also be observed from the experiment that above the threshold frequency, the ejection of photoelectrons from the emitter takes place with no time delay. Now let us discover what makes the photoelectric effect so important, and how it revolutionized our concept about the nature of electromagnetic wave or about the nature of radiation. Considering light as an electromagnetic wave, the following three experimentally observed characteristics of photoelectric effect cannot be explained. The first, stopping potential. According to wave theory of light, the energy carried by electromagnetic wave is directly proportional to the intensity of incident light. Therefore, the maximum kinetic energy of photoelectron and hence the stopping potential must be function of the intensity of incident light, or in other words, they must increase with increasing intensity of incident light. However, this perception is contrary to the experimentally observed behavior of photoelectrons. That is, the maximum kinetic energy of photoelectron is quite independent from the intensity of incident light. Rather, it depends on the frequency of incident light. Number 2, threshold frequency. Wave theory of light has no explanation for the presence of threshold frequency of light. Number 3, time. For a weak intense light, the wave theory suggests that a considerable time should be required to eject photoelectrons from the metal surface, whereas the experiments show that the ejection of photoelectron is spontaneous even for the faintest light. So the existing wave theory is unable to explain the experimentally observed feature of photoelectric effect. Something new was needed, and that new thing was put forward by Einstein. In the next video, I will explain the characteristic behavior of photoelectric effect through the idea of Einstein.